Hello, welcome to the part 4 of our video tutorial on how to master secrets of asynchronous programming. In the previous 3 parts, we've examined in a lot of detail the differences between so-called synchronous or sequential programming and asynchronous or concurrent programming. We've learned that it is more realistic to implement business logic that is discontinuous, that is not blocking, is not unrealistically putting everything on hold, that is acknowledging the nature of processing, which most of the processes are running simultaneously in parallel. And such approach brings many benefits as well as many disadvantages that we've discussed in the previous 3 presentations. Now we're going to look in more details into the challenge that we kind of hit at the end of the part 3. And that challenge is, how can we transform non-deterministic asynchronous program execution to become a deterministic program execution while avoiding synchronization? Because as we've seen in the previous presentation, we are faced with the problem of nondeterminism, whereby we cannot really predict the outcome of our processing as soon as we introduce latency and we relinquish control. So right now, we're going to have a closer look into the possibility of transforming non-deterministic program execution into a more solid deterministic, well-engineered execution. And like we said, by actually trying to introduce synchronization between 2 or more processes, we are kidding ourselves, because we are basically going back to square one and reintroducing continuous execution, which is fully sequential. So in other words, we need to figure out whether we can avoid non-deterministic behavior while at the same time avoiding blocking, which seems quite a challenge. The solution doesn't seem to be forthcoming in a straightforward fashion. So basically we see that blocking is not desirable because it really is taxing on many of the resources. So to actually avoid blocking, the only way to do it in a deterministic way is to avoid shared mutable state. We've seen in the previous presentation that shared mutable state is often considered to be the root of all evil, and is a very slippery slope, and leading us onto a thin ice, almost like a quicksand situation. Sometimes even we can use the word minefield, because when we have state that can mutate and is shared among more than 2 or more processes, then it's anyone's guess as to how consistent that state will be at any point in time. And this is a big problem. So again, in a more cartoonish way, shared mutable state is bad, okay? And we need to keep that in mind. Okay, so that's easy to say, but now what is not so easy is learning or figuring out how do we avoid shared mutable state, because it seems to be creeping up everywhere we look. The real solution, the real remedy, is to adopt functional programming, which is another flavor of programming, kind of the flip side of the imperative programming. So for those of you who are not familiar with functional programming or haven't spent much time doing it, just a quick refresher. In functional programming, we are basically following the mantra or the slogan, make let not var, which is the pun on the make love not war, John Lennon, Yoko Ono, great artists. And always keep that in mind, that when we are designing a program and coding the business logic, we should avoid using vars and switch over to using let instructions. So let's see what do we mean by that. We've seen that continuous execution via blocking is undesirable, and it is undesirable because it is wasteful, not only of system resources, but also wasteful on the resources known as end user's patience. So if we are blocking, we're introducing latency, and the end user is helpless, not capable of doing anything, just sitting there looking at the spinning wheel and hoping that eventually he'll get back the control into their hands. That is very frustrating and wasteful, and not very good for the business. The discontinuous execution, when we introduce asynchronous programming, for example in C# I mentioned we could use the await command, or this is potentially dangerous, as we've seen previously, because it risks us falling into the inconsistencies in shared mutable state. So the shared mutable state could end up being corrupt, which is not desirable. And the recommended approach would be to use both models judiciously. So there's no silver bullet or one size fits all. We cannot wholesale switch from one model to another. We need to consider continuing and discontinuing execution judiciously on a case-to-case basis. And I'm sorry again, there is no magic formula, but that's how things are, and we'll have to be cognizant of that fact. If we have a situation in our programming logic where we realize that continuous execution and blocking is acceptable, meaning it is okay to waste resources, both systems resources and end users' patience, because that type of processing makes perfect sense to be introducing latencies, then we are much safer switching to that deterministic model, because now we are not running the risk of having the shared mutable state corrupt. And the reason we mention that is because avoiding shared mutable state is harder than somebody who hasn't tried that might think. And oftentimes it is very challenging and very difficult to create a solution that does not involve shared mutable state. Now, there are many situations that we've seen where blocking is not acceptable, and that we have no other way but to relinquish the program execution control and switch to asynchronous processing. We need to immediately become aware of the fact that now we are stepping into a non-deterministic or less deterministic territory. And all the alarm bells and red flags should go off at that point. Any asynchronously processed shared mutable state is risky because it's non-deterministic. So if we are faced with that situation where we cannot avoid but must use asynchronously processed shared mutable state, then the only safe way to proceed is to switch to programming for immutability. So this is very important, and this is how we can gain some kind of a control back into our lives. So unfortunately, this most typically means that we are now being forced to abandon the good old familiar CRUD model: create, read, update, delete, which is kind of ingrained into so many developers' practices. And the reason we need to abandon the CRUD model is because it is relying on a database, and a database is a global instance of shared mutable state, where many processes are accessing that same state, which is mutable. And therein lies the problem of non-deterministic behavior. So when we get to that point, we need to switch from programming by using variables. So variables are bad, and switch over to programming by using values. So when we say let, we are defining a value. When we say var, we are defining a variable. So it is only us, as Smokey the Bear says, only you can prevent mutable data. There is no, again, magic bullet, silver bullet, or magic solution, magic potion. There is no philosopher's stone that could just magically prevent mutable data. It is a focused effort on the part of the designer and developer to get us there. The important aspect of this approach is that we always need to keep in mind that variables are mutable while values are immutable. So, for example, if we want to store user's birth date, then storing it using a variable is a bad approach, because variable is immutable, and the customer birth date is a fact that is invaluable. The recorded fact when somebody was born cannot change, because we haven't invented time machine yet, or may not be ever able to do it. But anything that transpired sometime in the past, was recorded, now becomes a fact, and the fact is immutable. And the fact is a value. So that birth date, that somebody was born on such and such a date, is immutable. It cannot change. If it changes, then we have a corrupt system that is not functioning according to the specifications and according to the expectations. So we see that one does not simply mutate a data structure. That is a very slippery slope, very dangerous situation. And we now realize that we have arrived at the world of concurrency with all its headaches and problems. And same as in real life, when we have many lanes functioning at the same time with merging and leaving and exiting or entering the highway, this is a very complex situation which we need to carefully design. Of course, we've seen that concurrent programming is very helpful in reducing latency, because there's no blocking, nobody's waiting on anything, things are just flowing and moving smoothly. This type of programming really scales well with CPU-bound computations. So if we have some beefy number crunching computation that must happen in a certain location, is not necessarily dependent on some other processes that are happening somewhere else, then this is localized within a single processing unit. In that case, a multi-core CPU would really come in handy, because we are not running the risk of corrupting a mutable state, because it's not shared. Then that situation helps us take advantage of parallel programming as it scales well. The concurrent programming is hitting some issues when we are dealing with I/O-bound computations, where more than one process is handling the mutable state, and they may, wait on each other, or may have to depend on each other. And as we've seen, this is where the bugs can creep in and the system becomes dysfunctional. Now, this brings us to another topic which I want to bring up here, is how do we deal with system deficiencies? Suppose we get called, because we are experts, we're software engineers. It happened to probably most of you viewing this presentation that sometimes we get called to look into a system that is misbehaving. So something is supposed to be working the way specification states, but it's not. There's a problem. So we may come have a look, but other team members are busy, and we are basically left to our own devices to sit down and examine the source code. So the source code is like a blueprint of the product that is actually running in a production environment. We can, if we sit down and examine the source code of any project, we can potentially arrive at three conclusions. There's three possibilities. The first conclusion would be that this source code obviously contains no defects. So everything holds water, everything is rock solid. We see all the logic is tight, and we can pretty much sign on a dotted line that no defects. It's very obvious. The second conclusion would be that the source code we've examined contains no obvious defects. We couldn't find any obvious defects. And the third and final conclusion would be the source code obviously contains some defects. So we found some error, programming error, or some error in logic that we can pinpoint. Here is where the logic is inconsistent, and therefore this is why the system is failing. Now, we can only claim that software obviously doesn't have some defects in case when the programming is following the deterministic logic, which means it is sequential. It represents continuous execution. In that case, we can either find an obvious defect, or we can say everything here is obviously correct. So let's look at Professor Rabbit's what does Professor Rabbit have to say about determinism? This is now the second take. The first one was in the part 3. So definition number 2 for the determinism would be, if we are claiming that a program is deterministic, it must have these two characteristics. If we record all the inputs that the program is capable of dealing with, when we replay those recorded inputs against the same program, we always get the same outputs. This is determinism. It is there is no variations. There is no loose ends. Everything is airtight. This is a good definition of determinism. Record inputs, you can replay them to your heart's content. Each time you replay them, you get the exact same outputs as previously. Now definition, this splits now into 2A and 2B. 2A says that the program is same executable deterministic if replay guarantees to produce the same results only when you run it on the exact same executable as the one the recordings were made. So exact same configuration, infrastructure and everything else. This is doable. However, definition 2B deals with cross-platform deterministic, which means we can record some inputs and outputs, and when we replay them, we expect them to show the same results on any platform, as long as source code is the same. That one is very difficult, because when we start changing the configuration and whatnot, even though the source code remains the same, we may experience different outcomes. And that is non-deterministic. So if the program is non-deterministic, for example, an event-driven program could be considered non-deterministic, then the best we can conclude by looking at the source code is that we cannot see any obvious deficiencies. That's the best thing we can say. We are not saying that there are no deficiencies. We're only saying that we cannot find them by examining the source code. However, even though we couldn't find any deficiency in the source code, we may expect them to appear during the actual program execution. Now, when you have a source code, a blueprint, it specifies certain things and the way things should behave. When you put them into a runtime environment, you may observe some surprises. This is what we call non-deterministic behavior. And this is due to, as I mentioned, the non-deterministic nature of the event-driven programming model. So when Professor Rabbit looks into sources of non-determinism, the main culprit is multi-threading. Enemy number one of determinism is multi-threading. With multi-threading, you should consider your program non-deterministic until proven otherwise, and it's very difficult to prove it otherwise. This is related to an observation that timings in different threads are not guaranteed, at least because of external interrupts. Okay, we are now dealing with a semi-chaotic situation that is related to events on the system, because we cannot engineer nor can we control the sequence of events that will get processed by the event-driven program. This is not controllable because the world does not obey a pre-programmed or predetermined pattern. The number of possible permutations and combinations of events, even in a modestly complex event-driven program, this number tends to be astronomical. You cannot create a finite list of all possible combinations and permutations. Obviously a problematic situation. Because of that, it is impossible to ascertain whether such program contains any deficiencies or not by merely reasoning about its logic from the source code. There's more to it than what you can glean from the source code. This makes concurrent asynchronous programming orders of magnitude more difficult than synchronous deterministic programming. No surprises there. This is basically what separates semi-chaotic situation from a very mechanical deterministic situation. Now, we need to keep this conclusion in mind anytime we're deciding whether to use synchronous and blocking continuous execution programming or to use asynchronous concurrent programming. It's a trade-off. So this gets us to the end of the tutorial. It is a very challenging and complex area of software engineering. So we will welcome any questions or inquiries to send to the digitalexpert@gmail.com. In the meantime, probably we should stay tuned for another series of tutorials that will be more hands-on or introduce more code samples illustrating the trade-offs that we mentioned here, when it's safe to use discontinuous execution, and when we have no choice but to introduce blocking with all the negative impacts on system resources and end user patience. Thank you for following me on this trail, and until next time, I hope you'll have fun and enjoy building quality software. Goodbye.